Today, we're diving into something that sounds incredibly niche, but I promise you, it's absolutely crucial. We are going to uncover the secrets of a tiny microscopic layer of material that literally holds the key to the next generation of global solar power. We're talking about counter-electrodes in perovskite solar cells. It's a component so fundamental that, honestly, without it, all the sunlight in the world wouldn't give you even a single watt of usable electricity.
Here is a quick look at our agenda for today. We'll start with the blueprint, move into the flawed gold standard, explore material alternatives, discuss the carbon electrode revolution, break down the physics of the match, and finally, look at the commercial horizon.
Okay, let's jump right into part one, the blueprint, the back electrode's role. To really get why this matters, we first need to understand what this critical layer actually is. Often called the counter-electrode, or just the back electrode, this is basically the conductive layer right at the very end of the line. Its main job? To collect charges from the transport layer and complete the electrical circuit. Depending on how the cell's internal layers are stacked up, this back electrode collects either positive or negative charges. So you can think of it as the ultimate gateway for all that energy being produced. If this gateway is closed or even just a little inefficient, well, the whole cell fails. Actually, think of this electrode like a highly secure highway toll booth, but one that has 6 vital jobs going on at once. It has to efficiently collect charges, sure, but it also needs to provide a low resistance contact so we don't lose that hard-earned energy as heat. Plus, it has to perfectly align its energy levels, act as a physical barrier blocking out moisture and oxygen, and on top of all that, provide mechanical stability. Ultimately, this single layer dictates the long-term stability of the entire solar cell. It's a pretty massive responsibility for a layer that's literally just nanometers thick.
Which brings us to part two, the flawed gold standard.
Now consider this massive number, greater than 26%. That is the staggering power conversion efficiency that labs have achieved using gold as the back electrode. When it comes to sheer performance, gold is just an absolute powerhouse, no doubt about it. But there's a huge tension here between what works in the lab and real-world manufacturing. Sure, gold gives us those record-breaking efficiencies and it pairs perfectly with transport layers. But the cons? They are enormous. The astronomical cost of gold is a massive barrier right out of the gate. Plus, applying it requires these insanely expensive vacuum chambers. And worst of all, under the hot sun, gold actually diffuses. It essentially melts right into the perovskite material, basically destroying the cell from the inside out. Talk about self-sabotage, right? It's just a complete non-starter for large-scale manufacturing. So, what about other noble metals? Silver and platinum seem like obvious alternatives. Platinum is super stable, but it's even more expensive than gold, so that's out for commercial use. Silver, on the other hand, is cheaper and highly conductive, but it has a fatal flaw. Silver literally reacts with the iodide present in these perovskite cells. That chemical reaction creates an insulating layer of silver iodide, which shoots up the resistance and causes rapid degradation. The cell basically self-destructs. Let's move on to part 3, exploring material alternatives. Since noble metals hit a total dead end for mass production, scientists have been desperately searching for new materials. First step in this search, transparent conductive oxides, or TCOs, like ITO and FTO. Now, these are fantastic if you want to build semi-transparent cells, bifacial ones, or advanced tandem architectures, where light literally needs to pass right through the cell. They give us good conductivity, sure, but they are incredibly brittle, which makes them a total nightmare to work with in flexible formats. Plus, they still require expensive vacuum deposition, and materials like ITO rely on costly elements like indium, so they aren't quite the universal silver bullet we need. We're also seeing a massive amount of global research iterating through other alternatives, like metal foils and conductive polymers. Things like copper and aluminum foils are mechanically tough and great for flexible roll-to-roll manufacturing. But the catch is they're highly prone to oxidation, metal diffusion, and corrosion. Then you have conductive polymers, which are lightweight and can literally be printed out, but they suffer from lower connectivity and limited stability. It's this constant tug of war trying to balance flexibility and cost against the risk of oxidation and poor electrical performance. And that brings us to part 4, the carbon electrode revolution. This huge industry bottleneck brings us to the rising star of our story. Enter what some are calling the carbon savior. We're talking about materials like graphite, carbon black, graphene, and carbon nanotubes. Carbon steps onto the scene as an absolute manufacturing miracle. It is ultra cheap. You can print it directly onto the cell without needing any expensive vacuum equipment. On top of that, it's highly resistant to moisture, it's chemically inert, and it's incredibly stable under heat. Now, carbon isn't perfect. We do have to accept a bit of a trade-off here. Its conductivity is lower than metals, which leads to higher sheet resistance, and you get a slightly lower open circuit voltage. So we take a dip in typical efficiency, hovering around 18 to 23%, compared to gold's 26 plus. But look at what carbon unlocks for us. It brings massive cost savings, true printability, and the environmental durability needed to actually survive on your roof through rain, wind, and heat for decades. Okay, let's look at part 5, the physics of the match. You might be wondering, why do some materials work perfectly while others fail so spectacularly? Well, it all comes down to a critical parameter known as the work function. In strict physics terms, this is the minimum energy needed to pull an electron out of a solid. But in plain English, think of it as a mandatory handshake, or like paying a toll booth fee between the back electrode and the transport layer. If those energy levels don't align perfectly, the electrical energy generated by the sun literally has nowhere to go. When the work function is a perfect match, like gold sitting perfectly aligned with its adjacent layer at 5.1 electron volts, charges just flow freely. You get lower contact resistance, efficient charge extraction, and a great fill factor. But if those energy levels are mismatched, watch out. It creates a devastating microscopic traffic jam. Charges just accumulate right at the interface, leading to recombination energy losses, reduced current, and ultimately a crippled low-efficiency solar cell. Finally, let's wrap up with part 6, the commercial horizon. Armed with an understanding of both the physics and the materials, let's see where the future of commercial solar is actually heading. When we stack these materials side by side based on the source data, the landscape gets very clear, very fast. Gold and silver have excellent conductivity, yes, but their cost is a total roadblock. But checking out carbon and composite materials, they offer incredibly low costs, excellent stability, and absolute dominance when it comes to scalability. We're even seeing emerging hybrid composite electrodes, like carbon mixed with metal nanoparticles, trying to blend the high conductivity of metals with the true affordability of carbon. And the choices between these materials have direct cascading effects on the final product. You can trace a straightforward chain here. Step 1, the conductivity of your chosen material reduces electrical losses, which directly dictates your power conversion efficiency. Step 2, contact resistance alters the interface quality, which locks in your fill factor. And step 3, the chemical inertness of the material, whether it reacts like silver or stays stable like carbon, literally dictates the lifetime of the device. Ultimately, commercialization lives and dies by economics. When you look at the harsh reality of manufacturing costs, from highest to lowest, it becomes overwhelmingly obvious why the industry is shifting. Gold, platinum, and silver sit right at the most expensive top. TCOs follow closely behind. But way down at the absolute bottom of the cost spectrum, that's where you find carbon and carbon paste. This economic reality is exactly why carbon-based and composite electrodes are currently the most attractive targets for commercializing perovskite solar cells on a global scale. So I'll leave you with this final thought. What matters more for the future of global energy? Achieving record-breaking, greater than 26% lab efficiencies with gold that we can never actually afford to scale? Or taking a slight efficiency hit to build a truly scalable, printable, and affordable product with carbon? Answering that question is exactly what will determine if perovskite solar cells become the dominant, world-changing energy source of our future.